Hello, everyone. Thank you for joining us this evening for week 3 of the Rise Institute and Rugby Research Injury and Prevention Group 2026 Analytics Series. My name is Alon Cooper. I'm a senior kinesiology major from Hampton University. And today, our first intern presenting will be Isabella, who is from California, and she will be presenting on confidence intervals. Isabella, if you will go ahead and introduce yourself and share your presentation.
Thank you, Elon, for the introduction. Yes, my name is Isabella Perez. I'm a junior that attends Downey High School in California, and today I'll be presenting on confidence intervals, what it means, how it's built, and common state mistakes to avoid. So I'm going to share my screen. Okay, I'm going to begin. Oops. Okay, so to begin, in research, a single number point estimate alone is incomplete and is typically considered a guess because a different sample would have given a different set of numbers as well. So while this odds ratio of 0.75 looks precise alone, with its interval 0.70 to 0.80, you know how much to trust it. So that's why journals require it, or else it's basically unpublishable because reviewers wouldn't know how seriously to take the data. So 95% confidence does not mean 95% chance the answer is in this range. It means if you repeated the study this many times, 95% of the intervals you build would contain the true answer. So it's like a net being casted the same way each time to catch fish. 95% of casts catch the fish, and any one cast either caught it or didn't. So the method is what's reliable, not a single try. So, sorry, was I on the wrong side? I apologize for that. I'm going to refer to this equation now. So formally putting it, this formula here is the mathematical definition of theta. Theta is the true value you are trying to find, and it's fixed, even though you can't see it directly. It is basically the fish we are trying to catch that is under the water. So additionally, the symbol on the far right that looks like an A is called the significance level, and it stands for how often you're okay with missing. So for example, 5% for a 95% interval. And on the other hand, 1 minus A is the flip side, succeeding 95% of the time. So once you've actually got your interval, there's no more randomness left, and theta is either in or it isn't. And last thing, L and U stand for the lower and upper ends of the data collected as a whole. So how you build the interval. So I just want to note that there are several versions of a formula I am presenting here to find the confidence interval, and it all adapts and changes depends on what you're estimating and how much you know. So I'm using the general formula. And we're moving on. Theta, as I mentioned earlier, is the true value you never see directly. And theta hat right here is your best estimate of theta, the true hidden value from your data. So every interval is essentially your best guess, plus or minus some wiggle room, such as 50, give or take 5. So 45 to 55 would be your intervals, and theta hat is the 50. And important to note, the standard error, which is the SE on the far right, is how much your estimate naturally bounces around, which is the 5. So the critical value C or T value for small samples controls how wide the wiggle room is. So for example, that would be 1.96 for 95%. So by seeing it in practice, I just want to clarify some vocab before I explain the published data. Minting stands for making a coin, and mean minting year is the average year across a batch of coins. So this figure shows 1,000 resampled estimates of that average from 50 pennies. And the middle 95% of those estimates between the two lines is the confidence interval itself. So the formula presented on the bottom of the slide is coming from the formula I presented on slide 4, but I'm assuming more on what's inside the margin. So to start off on our standard error, it basically dictates the wiggle room part of your interval. So how far the data can stretch. So furthermore, n is just your sample size, so more data shrinks the margin, but only by the square root of n. So 4 times the data only halves it, so more variability in the data widens it. So if you want a higher confidence, such as 99% versus 95%, that widens too. And there's a few mistakes people make when they're doing this type of research. One, treating 95% as a probability about the answer and not the method. Two, confusing this with a Bayesian credible interview. They are a different framework and they're a different question that I will not be covering in this presentation. And three, assuming 2 intervals overlapping means no real difference. So let's say you're examining 2 groups instead of one, the no difference is not true because let's say, for example, 10 to 20 and 18 to 28 overlap, but one estimate is clearly higher. So to check if 2 groups differ, test the difference directly. And a few takeaways, it's important to report the range and not just the number. So if it's 95% confidence, it's about the method's reliability, not about the odds this one interval is correct. And confidence interval is not a credible interval. These are my references, and that concludes my presentation. Are there any questions?
Yes, thank you so much, Isabella, for that presentation. Dr. Lopez, would you like to add anything?
So a couple of points. Thank you so much, Isabella. You did a great job on the presentation. And more importantly, it is, what I wanted to say was, obviously there's a couple facts we're going to talk about, but in the bigger picture of things, and I think, we can comment on this. The one thing that a lot of people don't understand is that if you have a very, very narrow confidence interval, you can almost exclude the necessity of calculating the p, value, because it means it's validated. The data has accuracy that, so the narrower the confidence interval, the stronger chance. And again, I don't want to get too much into the weeds with this, but obviously when you're discussing, confidence intervals, I'm sure you probably came across this, Isabella. There's like standard error calculated versus standard deviation, prediction intervals. And, it's just population mean versus individual data points. It's just, I guess, a better way of, the accuracy method. They call it the accuracy method, for confidence intervals using a standard error, right? It measures precision of the sample, right? The population. And then obviously the standard deviation confidence interval measures the tolerance range of how wrong you could possibly be with your population of cohort within your range, So I just wanted to bring those up because a lot of people, often see that, and they, there's 2 different ways of, analyzing the confidence interval. And then also, you can validate. And this is, I actually was just talking with someone who was doing a systematic analysis. And I told him, I said, you could validate, your data further. So basically everything can be reanalyzed to validate it a little bit more. And obviously, even if you have a small cohort, so you can, validate that in some capacity. So, you can check your, assumptions checking, bootstrapping, and coverage analysis. Those are 3 ways of validating confidence intervals. So you can actually so say if you have a weird outlier and it's just distorting your confidence interval, but it's approaching significance. So it's almost like your p-value is almost 0.005, 0.05, but it's almost like 0.06 or 5, 2, 5, 3. You want it to be less than 0.05, but if it's approaching significance, you can validate it and try to prove you have significance there with a narrower confidence interval, aside from just using the p-value. Okay? So there's just some things you can do And like I said, we can go into the differences, of uh, bu- 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 yeah, those are the two I probably would leave with you, those 2 points, because those are the two biggest important points. You know, and then obviously they do kind of emphasize the interpretation of confidence intervals for research or clinical trials versus research in general. And that's something we'll talk about another time. All right, everyone.
Our second intern to present today is Hunter. He will be presenting on hypothesis testing and p-values. Hunter, when you have the chance, will you introduce yourself and share your screen?
Thank you, Lon, for the introduction. I'm Hunter, and I will be presenting on hypothesis testing and p-value. So this is my presentation on hypothesis and p-value. So before I start my presentation, I'm going to kind of define some important terms. So hypothesis testing is a method for validating assumptions and correlations, and this is based on the sample data that comes from experiments and that kind of thing. And p-value helps with measuring consistency with the null hypothesis, which I will explain later. So how do you get a p-value? So p-values can be derived from multiple different statistical tests that follow normal distributions. And here I have some examples. So the t-test measures gives a p-value of the difference between the two populations, the mean of two populations. The z-test measures the correlation between a sample from a population and the mean of the overall population. And then chi-squared, as Aaron mentioned in an earlier presentation, um, shows compares expected results to observed results in the experiment. And these will all give you a p-value. So what does this p-value tell us? When when you create an experiment, a statistical experiment, you have a null hypothesis and an alternate hypothesis. A null hypothesis typically says that there is no correlation or that there's no real change, and an alternate hypothesis says otherwise. Now, when comparing, and now after calculating a p-value, the p-value is compared to an alpha value. And for this example, I'm showing a chi-squared table. And for the p-values here, we have 0.05 and 0.01, and those are kind of how confident it is. And the smaller these will be the alpha values, and the smaller they are, the more confident there is. And then the degrees of freedom, and these are kind of the values that will be compared to one after calculating a p-value. And if the p-value is greater than these numbers, then you fail to reject the null hypothesis, meaning that the null hypothesis is most likely correct in describing the relationship between whatever you're measuring, and if it's less than or equal to this value, then the null hypothesis is rejected, and the data is supporting the alternate hypothesis and their significance. So why does p-value matter? So p-value, like I said, evaluates the statistical significance of certain data points. So when example I will use throughout this presentation is with placebo and creation of new drugs. What typically new drugs are tested with compared against a placebo, and if there's a statistical significance between the treatment and the placebo, then it shows that the drug is actually doing something to help the patient rather than just the belief that the placebo effect in which the patient just believes that something is happening and it's has a slight impact. Another important point is that it helps evaluate the probability of random chance. And typically if there's a very low p-value that is below the 0.05, it means that the results probably not due to random chance. There's such a low probability that happening that it's not fair to reject the null hypothesis. So, and this is very important because statistics are very valuable in many different fields. So, like I've been talking about the placebo effect in medicine, there's also businesses use it to evaluate the effect on their policies on the effect of sales, whether different promotional pitches are working on and are generating greater revenue, or in public policy and seeing the effect of policies on society, and seeing the impact. So, but there are limitations of using p-value. There are two types of errors that I'm going to talk about. Type 1 error, which is when the data rejects a true null hypothesis. So this means that the data finds that there is a correlation or there is statistical significance when there really isn't. Or type 2 error, which is accepting a false null hypothesis, meaning that this data finds a null hypothesis to be true when it should find the alternate hypothesis to be true. And these mistakes typically stem from biased data or mistakes in calculations. In addition, the standard is typically found to be 0.05 as the p-value as the p-value marker. But this is according to the National Institute of Health, this p-value origination of this p-value was very arbitrary, and it was first introduced by Fisher in 1920, and he never meant for it to become the standard for any type of research. Um, and also, another misconception about p-value is that greater p-values show greater significance, and this is not true. Smaller p-values just mean that there's a greater confidence that it is significant, not that there's a greater margin. So, for example, just because the placebo and the treatment are statistically significant, it doesn't mean um, the difference in p-value between two treatments is small. One of them is smaller, doesn't mean that the second one is even more effective than the first one. And this kind of leads to the next point, is that whether the difference is actually practical. So there might be statistical significance. The p-value may say that there is statistical significance. However, this might not be very practical or applicable. So using the placebo and drug treatment, maybe it only reduces symptoms by a little bit, and it doesn't really have real application in real life. So my takeaways are that p-values are still important to understand statistical significance. Like I said, it's derived from different statistical tests and rejects null hypothesis or fails to reject them, and shows whether there is real correlation. And then, but the National Institute of Health also says that effect sizes should also be reported, as they're more representative of the magnitude of difference, which is important. And as for the use for RIPG, a lot of what the research that we will be doing this year is evaluating trends and correlations, trying to see if there is a cause and effect relationship between certain factors and injury. And for example, this could be comparing the occurrence of injury on turf versus grass and seeing the statistical significance of that. These are my references, and thank you for listening to my presentation.
All right, thank you so much, Hunter. Does anyone have any questions, or Dr. Lopez, would you like to add anything?
No, great job there, Hunter. Obviously, and not only that, Lily, Izzy, you guys are doing a great job of trying to distill in a way for everyone to kind of understand. And as I said before, p-values, everyone hangs their hat on that, but that's just one part of the bigger picture of validating data. When you have a good data set, that also benefits you, because then you can get stronger confidence intervals from that, that'll be narrower, or depending on what you're doing, errors or prediction wants wider confidence intervals. But the more important thing is, it doesn't measure just like p-values give you some validity, but you could also measure the effect size. You can see the sample size illusion, or there's other replication, as other stuff that you can do. It's not alone that p-value can be done. So you want to make sure you understand that it's part of the puzzle. And that's why when we do, and I'm sure you guys all saw our papers, when we put our papers together, we include all the variables. We include the incidence. We include the confidence interval. We include the p-value. We include the exposure. This way, there's no question. If someone wants to replicate our analyses, they can. They can just take the data and crunch it themselves if they wanted to. We don't hide behind the data and give out only one or two pieces, or maybe just the validity of it. So you need to kind of, for the validity of it, you can use all that you have. And obviously that just benefits things. Mr. Pruitt, do you have anything to add to that, or how are we doing there, sir?
I think these are two very good presentations so far, and I think it's a good start to, well, I am just joining today. I don't know how long you guys have been going, but it's a good start to the summer for hitting some of the foundations of biostatistics. So, like you said, there's a lot of different ways. I hate using this term, but to skin a cat. But it's a lot of different pieces to the puzzle.
Yeah, it is interesting. I think what Mr. Pruitt's trying to emphasize is that you can analyze different data sets to achieve what you're looking for. And you can look at different data sets through various lenses when you're trying to analyze it for a particular variable or a covariable, or maybe if you're looking to, validate something on top of that. It's important for you to understand what your goal is with the data on that note. All right, everyone.
That will conclude our call for today. Thank you, everyone who joined the RISE Institute and Rugby Research and Injury Prevention Group Analytics Series. Thank you, everyone, for joining us.